and get you informed fast. Today we're looking into a field that, well, it affects everyone, every day. Food science and technology. What really goes into understanding food before it even gets near your plate?
Right. It's this whole world built on some pretty complex principles. It's much more than just cooking or looking at a nutrition label. Think science meeting the kitchen, but, scaled way up industrially.
We've got an interesting mix of sources for this. There's a university curriculum for food technology, really detailed. Then this great explanation of calculus using a story, which I liked.
Oh, yeah.
Yeah, and some insights on how complex science gets simplified for teaching, plus a look at typical student questions about the field.
Okay, so our mission here, for you listening, is really to unpack the science and math foundations of food tech. Why are they so critical, and how are these sometimes tricky ideas made graspable? The aim is for you to get what's key here, efficiently.
Okay, let's dive in with that curriculum outline first, because, wow, the first thing that hits you is just how broad food technology is. It's not just one narrow thing.
No, not at all. It really spans a huge range. You've got the core sciences you might expect, like food microbiology, understanding microbes in food, the good and the bad.
Right.
And food chemistry and nutrition, the food's makeup, how it changes, plus food analysis, figuring out exactly what's in there.
But then it branches out into all these super specific processing areas, like dairy processing, baking, confectionery,
Fruits and vegetables, meat, fish, poultry processing.
beverages, milling, even emerging tech. It's a massive list of different materials and ways to handle them.
And crucially, underpinning all that processing is the engineering side. The curriculum hits that hard.
Yeah, I saw courses like food process calculations, principles of fluid mechanics.
Fundamentals of heat and mass transfer, unit operations for food industries, refrigeration and cold chain, storage engineering. I mean, this is where the physics and math really kick in.
And on top of that, the outline lists things like safety, quality control, regulations, making sure it's all safe and up to standard. Plus, the more creative side, new product development, food waste management, even genetic engineering.
It's clearly rigorous. Some of the source materials, student discussions, they confirm that. Students know it's a tough degree.
And that rigor seems tied directly to needing these fundamental science and engineering principles for all those different areas, right?
Exactly. Doesn't matter if it's milk or a new veggie burger, the underlying mechanics, the physics and chemistry, they're key.
Okay, this is where it gets really interesting for me. How do you actually handle processing such different things? Liquids like juice, solids like grain, delicate stuff like fruit. You said it comes back to physics and chemistry.
Precisely. Look at courses like fluid mechanics or heat and mass transfer. They're not just theory. Fluid mechanics, that's about how liquids and even gases flow. You learn about properties like viscosity, how thick something is, how fluids act in pipes or when you're mixing them and pumping them.
So understanding fluid mechanics is essential for just getting juice into bottles consistently.
Exactly. Or making sure your soup doesn't separate later because it wasn't mixed right initially. You have to predict and control that flow.
Okay. And heat and mass transfer. That sounds like it's everywhere in food.
Oh, it's fundamental. Pretty much every process involves it.
Like cooking, obviously. Or freezing.
Absolutely. You're learning about conduction heat moving through a solid, like in a pan, convection heat moving in air or liquid, like in a convection oven, and radiation, like heat from a broiler element. And you apply all that to design things like heat exchangers, refrigerators, ovens, the core equipment for preserving, cooking, cooling food safely and efficiently.
At food process calculations, it seems to tie things together. The curriculum mentioned energy balance, enthalpy changes.
Yeah.
Sounds like thermodynamics.
It is. Core thermodynamics. Energy balance is basically tracking energy where it goes in a system, like a pasteurizer or a dryer, in, through, out. Enthalpy is about the total energy in a substance. You need these calculations to know how much energy a process takes, how long heating or cooling will take, how much steam you need. It's the physics of scaling up efficiently.
Got it. And unit operations, that term came up too. Filtration, extraction, distillation.
Think of unit operations as the standard toolkit, the basic building block steps used across lots of industries, definitely including food.
Okay.
Filtration, separating solids and liquids. Extraction, pulling something out, like making coffee or getting oil from seeds. Distillation, purifying liquids. These are classic chemical engineering techniques, just adapted for food. Understanding them means understanding the physics and chemistry making them work.
So connecting all these dots, the flow, the heat, the reactions, the separation, it really seems clear you need a common language, a way to measure and predict. And that's got to be math.
That's exactly it. The curriculum shows this clearly. Courses like probability and statistics super useful for quality control, dealing with variations in data, and even more advanced stuff like transforms and partial differential equations. These are tools for modeling complex changes over time and space.
Like how heat moves through a big piece of meat, or how a reaction spreads.
Precisely. And then, of course, there's calculus, explicitly listed, differential, integral, multiple integrals.
And we saw in the sources, students ask about the math load. It's definitely seen as a hurdle, or at least a key part of the rigor.
It absolutely is. Calculus is, well, it's fundamental for understanding rates of change and accumulation. And you see those concepts everywhere in food processing.
Yeah, that calculus analogy source was helpful here. The story about Bob and the broken bridge, it made it click a bit more.
It's a great analogy. It explains differentiation first finding the instantaneous rate of change, like the slope, the steepness of a curve at one single point. Bob needs to cross a gap on a fallen tree. He wants to know how steep it is right where he's about to step.
Right, not the average steepness, but right there. And he uses pebbles to measure a tiny rise overrun.
Exactly. He's finding the slope of just a tiny piece. And the idea is, if he could use infinitely small pebbles like sand grains, he'd get the exact steepness at that one point.
That's differentiation, finding out how fast something's changing at one specific moment.
Yep. How fast is temperature changing? How fast is a reaction going? Differentiation helps model that instant change.
Okay, then the story switched to integration. That was about finding the total amount or the area of an irregular shape.
This happens when a piece of the bridge falls onto the grass the deer eat. Bob needs the exact area covered to know if they still have enough food left.
And he starts by guessing with big pebbles, then smaller ones.
Right, better approximations. But to get the exact area, he imagines covering it with infinitely tiny grains of sand and just adding up the area of every single grain. That's integration, summing up infinite tiny parts to get a total.
So like finding the total volume in a weirdly shaped tank, or the total heat absorbed during cooking, or the total amount of product from a reaction.
Exactly that. Those are all integration problems in food tech. Differentiation and integration are the tools for analyzing change and accumulation in all these dynamic food systems.
Okay, it's undeniable this field is broad and needs you to grapple with some complex science and math. One source about science tutoring mentioned this can feel overwhelming, which ties back to those student questions about math, probably.
Oh, it definitely can seem daunting. But that same source also talked about how these concepts get taught effectively, how they're simplified. It's not just about dumping information.
Using the right tools, you mean? Like breaking things down.
Yeah, that's key. Tutors break big topics into smaller, manageable chunks. And visual aids. The source noted visual info gets processed way faster. Think diagrams of fluid flow, animations of heat transfer, charts showing reaction steps.
That makes total sense. Seeing it helps more than just reading abstract descriptions. What about hands-on stuff?
Absolutely crucial. Applying the theory makes it stick. And if you look back at that curriculum, it's packed with labs. Microbiology lab, chemistry lab, unit operations lab, engineering practices lab.
Right.
Those aren't just for show. That's where you actually see fluid mechanics with pumps, or heat transfer with exchangers, or try filtration yourself. That practical experience makes the theory real.
And analogies like the Bob story for calculus, or the tutoring source mentioning comparing reactions to baking a cake.
Analogies are bridges. They connect these abstract ideas to something you already know, something familiar, makes it feel less strange, more intuitive. These simplification techniques are vital for mastering a field like food technology.
So let's pull this all together for you, the listener. What this deep dive shows is that food technology is deeply interdisciplinary. You absolutely need a solid footing in chemistry, biology, physics, and critically, math and engineering.
Yeah, that curriculum we looked at isn't just a random list. It's a roadmap showing how these fundamentals connect, how they're essential for everything from ensuring food safety with precise temperature control,
To making production lines efficient, using process calculations.
to even innovating new products by really understanding ingredient chemistry. It all ties back.
And while the concepts themselves might be complex, the way they're taught breaking things down, using visuals, hands-on practice, relatable analogies, it's all designed to help you handle that complexity. To really get the concepts and gain the knowledge properly without, feeling totally lost. Understanding why the math and science are there gives it all context.
It's really about giving professionals the full toolkit they need for what is, let's face it, a completely vital global industry.
So we've seen how this practical world of getting food to us